And now in this lecture I will answer two questions. In the first question we find out the perimeter of this quadrilateral ABCD, and in the second question we'll find out the area of this green shape. So we start with the first question. In the drawing we have quadrilateral ABCD. We know that PQ equals to 20 units in its length. This is 97 QC, that equals to 40 units in its length. And this is a right angle, this is also a right angle, and this is a right angle. We know also that BQ equals to 10 units in its length, PQ equals to 20, and QC equals to 40 units in its length. And our task is to find out the perimeter of this quadrilateral ABCD. So, what is the definition of a perimeter? A perimeter of a quadrilateral is the sum of its four side lengths. That is to say, it equals to AB plus AD plus DC plus CB. Okay, so we have to find out the sum of its the side lengths of this quadrilateral ABCD. So first of all, we will do a construction. That is to say, we will draw a perpendicular on AD at point P. Again, we will draw a perpendicular on AD at point P. So actually, this angle equals to 90 degrees in its side, and this angle also equals to 90 degrees in its side according to our construction. We will extend that perpendicular from point P until it touches side BC. And we define the touching point of the extended perpendicular P with side BC. This point is point M. By doing this construction, we have here those two angles are defined as one-sided interangles. The sum of those two one-sided interangles is of course equals to 180 degrees. And because of the fact that the sum of those two one-sided interangles is equal to 180 degrees, it means that they must be located between parallel lines. That is to say, AB is parallel to PM, according to Rule 18. And again, because of the fact that the sum of those two one-sided interangles is equal to 180 degrees, they must be located between parallel lines. That is to say, AB is parallel to PM, according to Rule 18. So, quickly on Rule 18. According to Rule 18, if the sum of two one-sided interangles is equal to 180 degrees, then they lie between parallel lines. In the drawing, we have those two angles that are defined as one-sided interangles. If we know that the sum of those two one-sided interangles is equal to 180 degrees, this is to say, if alpha plus beta equals to 180 degrees, then line A is parallel to line B. Then it must be located between parallel lines. That is to say, line A is parallel to line B. We already implemented Rule 18 in our drawing because someone mentioned the sum of those two one-sided interangles is equal to 180 degrees, and therefore they are located between parallel lines. That is to say, AB is parallel to PM. So according to Rule 18, AB is parallel to PM. Likewise, the sum of those two one-sided triangles is also equal to 180 degrees, and therefore those two angles must be located between parallel lines. That is to say, PM is parallel to DC. Yeah, PM is parallel to DC according to the same rule, Rule 18. So PM is parallel to DC. Likewise, the sum of those two one-sided triangles is also equal to 180 degrees, and therefore they must be located, those two one-sided triangles, they must be located between parallel lines. That is to say, AB is parallel to DC. AB is parallel to DC. So in total, we actually found out that according to Rule 18, the three line segments AB, PM, and DC, they are parallel to each other. That is to say, AB is parallel to PM, and PM is parallel to DC, and also AB is parallel to DC. Okay? So, whenever you have three or more line segments that are parallel to each other, and they are connected by AD and BC. Again, the three parallel lines AB, PM, and DC, they are connected together by AD and by BC. So whenever you have three or more parallel lines that are connected by other two line segments, then the following relationship exists between the two line segments that connects the three parallel lines together, according to the basic proportionality theorem. Repeat again. Here we have AB is parallel to CD is parallel to DE. And we have here line A and line B connects the three parallel lines together. Then the following relationship exists between those two red lines that connects the three parallel lines together. The relationship is as follows: AC over CD equals to BD over DE. Again, AC over DC equals to BD over DE. This is according to basic proportionality theorem. So we can implement the basic proportionality theorem in our drawing. Why? Because in our drawing we have three parallel lines. That is to say, AB is parallel to PM is parallel to DC according to Rule 18, and line segment AD and line segment BC connects the three parallel lines together. And therefore, according to the basic proportionality theorem, the following relationship exists between line segment AD and line segment BC that connects the three parallel lines together. The relationship is as follows: AP over PD equals to BM over MC. So, write it down. So, according to the basic proportionality theorem, the following relationship exists between the parallel lines AD and BC that connects the three parallel lines together. AP over PD is equal to BM over MC. And again, according to the basic proportionality theorem, the following relationship exists between AD and BC that connects the three parallel lines together. AP over PD equals to BM over MC. Actually, it is given us the question that AP equals to PD again. AP equals to PD according to what is given us the question. So if we define the length of side AP as x, then side PD must be also equal to x because they are equal to each other. Again, AP equals to PD according to what is given as the question. So when you substitute AP by x, PD also equals to x because they are equal to each other. So it is x over x equals to BM over MC. X over x is 1, so 1 equals to BM over MC. Here we will multiply this equation by MC, and finally we will get that MC equals to BM. So if you found out that MC equals to BM, that is to say, at point M, side BC has been bisected into two halves. And again, at point M, side BC has been bisected into two halves. The first half is BM, and it is of course equals to the second half MC, and each half of MC must be of course equals to BC over 2. And again, at point M, side BC is bisected into two halves. The first half is BM, and it is also of course equals to the second half MC. Each half must be equal to BC over 2 because BC is being bisected into two halves. BC in total equals to 10 plus 40. BQ is 10, QC is 40. 10 plus 40 over 2. 10 plus 40 is 50, and 50 over 2 is 25. So in total, we actually found out that BM equals to MC equals to 25. That is to say, BM equals to 25 units in its length. MC also equals to 25 units in its length. So what is the length of this line segment QM? From the drawing, it is very easy to see that QM in total equals to BM minus BQ. Repeat again. QM in total equals to BM minus BQ. So QM in total equals to BM, that is 25, minus BQ, that is 10. 25 minus 10 is 15. So in total we found out that QM equals to 15 units in its length. This is the small segment QM that equals to 15 units in its length. In the next step, we will implement the Pythagoras theorem on this right green triangle PQM. And again, we will implement the Pythagoras theorem on this green right triangle PQM. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Again, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle PQM, here by PT is the abbreviation for Pythagoras theorem. So in the right triangle PQM, PM squared, that is the square of the PM squared, that is the square of the hypotenuse, is equal to QM squared plus QP squared. And again, according to the Pythagoras theorem, in the right triangle PQM, PM squared, that is the square of the hypotenuse, equals to QM squared plus QP squared. PM is the missing side, so electricity, so it is Pm square equals to Qm square. Qm is 15, therefore Qm square is 15 squared, this is 225 plus Qp square. Qp is 20, and therefore Qp square is 20 squared, that is 400. So in total, we have found out that Pm square equals to 225 plus 400, that is 625. Repeat again, Pm square equals to 625. Here we take out of this equation and find out that Pm, the missing hypotenuse Pm, is equal to the square root of 625, that is 25. Pm equals to 25 units in its length. This is the hypotenuse Pm, that is equals to 25 units in its length. In the next step, we will do another construction. That is to say, from point M, this point M, we will draw perpendicular on DC. Again, from point M, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We will define the touching point of the perpendicular from point M and DC. This point is point N. So by doing this construction, we get the quadrilateral PM and D. Inside this quadrilateral PM and D, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral PM and D we have 4 right angles, and therefore it is a rectangle. We define the size of this angle QPM. This angle is alpha. So in the green triangle, the green right triangle PQM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. BC is one side of a quadrilateral ABCD. So BC is the side of a quadrilateral, it is absolutely a straight line. So if you focus on the right side of the straight line BC at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line BC at point M? You have this angle that is equal to 90 degrees minus alpha, plus this angle that is 90 degrees. 90 degrees minus alpha plus 90 degrees is 180 degrees minus alpha, plus the missing angle in total must be equal to 180 degrees according to rule 3. Therefore this third missing angle must be equal to alpha. Why? Because 180 degrees minus alpha plus alpha is 180 degrees. That is the sum of the angles on the right side of the straight line BC at point M according to rule 3. Therefore this third missing angle must be equal to alpha. So in the right triangle M and C, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. According to the same rule that says the then the sum of the angles in a triangle is equal to 180 degrees. Okay. In the next step, we'll prove that those two right triangles can go into each other according to angle side angle rule. That is to say, the right triangle PQM can go into this right triangle MNC according to angle side angle rule. So why the green triangle PQM can go into this triangle MNC? First of all, we have those two angles are both equal to alpha and therefore they are equal to each other. In addition, side PM of this green triangle QPM equals to 25, and it is equal to side MC of this right triangle MNC. MC also equals to 25 in its length. So those two sides are both equal to 25 and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So actually proved that those two right triangles can go into each other according to angle side angle rule. That is to say, we actually proved that those two angles and the side that is included between those two angles, that is actually side PM, this green triangle PQM are correspondingly equal to those two angles, and the side that is included between those two angles, that is side MC, this right triangle MNC. And therefore, those two right triangles can go into each other according to angle side angle rule. So I write it down. We actually found out that the green triangle the green right triangle PQM congruent. This is the sign of congruent to the lower green to the lower right triangle MNC according to angle side angle rule. So prove that those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we will derive that those two sides must be also equal to each other in their lengths, according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding sides must be equal to each other in their lengths. But QP is 20, therefore the corresponding side MN must be also equal to 20 units in its length. So MN equals to 20 units in its length. Likewise, according to the sum rule, those two sides must be also equal to each other. Again, according to the sum rule that said that corresponding sides and congruent triangles are equal to each other. Therefore, side QM equals to 15, and it must be equal to the corresponding side NC. That is to say, NC must be also equal to 15 units in its length. We already found out that PM and D is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PM and D, side PM is equal to the opposite side DN. But PM is 25, and therefore the opposite side DN must be also equal to 25 units in its length. So DC in total, side DC of quadrangle ABC in total is equal to 25 plus 15, that is 40 units. Okay. Likewise, according to the sum rule, in the sum rectangle PM and D, side MN must be equal to the opposite side PD. But MN is 20, therefore the opposite side PD equals to X must be also equal to 20 units in its length. PD equals to X equals to 20 units in its length. But AP also equals to X. And therefore X must be also equal to 20 units in its length. So we actually found out all the three sides of the length of all the three sides of quadrilateral ABCD. AB in total is 20 plus 20, that is 40. DC in total is 40. And BC in total it is 10 plus 40, that is 50. The only missing side is side AB. After we find out the length of side AB, we will be able to find out the perimeter of this quadrilateral ABCD. So in total, 40 plus 40 is 80. 80 plus 50 is 130. So 130 plus the missing side AB is equal to the perimeter of this quadrilateral ABCD. Repeat again. The perimeter of any quadrilateral equals to the sum of its four side lengths. So AB is the only missing side that is left to find out. So here we use another new rule, that is the rule of trapezoid mid-segment theorem. What is the trapezoid mid-segment theorem? First of all, quadrilateral ABCD is a trapezoid. Why quadrilateral ABCD is a trapezoid? Because in quadrilateral ABCD, we already found out that side AB is parallel to side DC. Again, AB is parallel to DC according to rule 18, and therefore quadrilateral ABCD is not only trapezoid, but it is a right angle trapezoid. Why quadrilateral ABCD is a right angle trapezoid? Because first of all, AB is parallel to DC, and those two angles are both right angles, and therefore quadrilateral ABCD is one side is right angled trapezoid. Okay. So what is the trapezoid mid-segment theorem? According to trapezoid mid-segment theorem, if a line segment connects the midpoints of the legs of the trapezoid, then it is parallel to the bases, and its length is equal to half of the sum of the lengths of the bases. This is trapezoid ABCD. That is to say, side AB in quadrilateral ABCD, side AB is parallel to side CD. This is side point E. Point E is the midpoint of AC. Again, point E is the midpoint of AC. Likewise, this is point F. Point F is the midpoint of BD. That is to say, BF equals to FD. Likewise, point E is the midpoint of AC. That is to say, AE equals to EC. Line segment EF connects the midpoints of the legs AC and BD by side line. Again, line segment EF connects the midpoints of AC and BD together by side line. And the trapezoid mid-segment theorem answers on the question, what is the length of EF? EF equals to the sum of its two parallel bases, that is to say, AB plus CD over 2. Again, EF equals to the sum of its two parallel bases over 2. So EF equals to AB plus DC over 2. Okay, again, EF equals to the sum of its two parallel bases over 2. That is to say, it is AB plus DC over 2. So we can implement the trapezoid mid-segment theorem in our drawing. Why? Because in our drawing, this is point P that bisects AD. Why? Because AP equals to PD. So point P is the midpoint of AD. Likewise, point M is the midpoint of BC. Why point M is the midpoint of BC? Because BM equals to MC. That is to say, at point M, BC has been bisected into two halves. The first half is BM, and the second half is MC. And of course, BM equals to MC. Again, at point P, AD has been bisected into two halves. The first half is AP, and it is of course equals to the second half PD. Each half equals to X. So actually, line segment PM bisect side AD, bisect the leg AD, and 9:07 p.m. also bisect the leg BC. So, what is the length of PM according to trapezoid mid-segment theorem? PM equals to the sum of its two parallel bases, that is to say AB plus DC over 2. Again, PM equals to AB plus DC over 2. So, I write it down. So, according to the mid-segment, trapezoid mid-segment theorem, PM, as I already mentioned before, PM bisect AD into two halves, and PM bisect the leg BC into two halves. Therefore, PM is the mid-segment of trapezoid ABCD. And according to trapezoid mid-segment theorem, the length of PM is equal to the sum of its two parallel bases, that is to say AB plus DC over 2. And again, according to the trapezoid mid-segment theorem, the length of mid-segment PM that bisects the two legs of trapezoid ABCD equals to the sum of its two parallel bases, that is to say AB plus DC over 2. But again, that AB is parallel to DC, according to what we already found out, that AB is parallel to DC, and therefore quadrilateral ABCD is a trapezoid. Because the definition of a trapezoid is a quadrilateral with one pair of parallel sides. In quadrilateral ABCD, side AB is parallel to side DC, and therefore quadrilateral ABCD is a trapezoid. So the two parallel bases are AB and DC. And the length of the mid-segment PM equals to the sum of its two parallel bases, that is to say AB plus DC over 2. But we already found out that PM equals to 25, so we can substitute PM by 25. So PM that is 25 equals to AB. AB is the missing side, so leave this it is. AB plus DC. DC in total equals to 25 plus 15, that is 40. So this equals to 40 over 2. So in total we found out that 25 equals to AB plus 40 over 2. Here we will multiply this equation by 2 and finally get that 25 times 2 is 50, so 50 equals to AB plus 40. Here we subtract 40 from this equation and finally get that the missing side AB is equal to 50 minus 40 is 10. So AB equals to 10 units in its length. AB equals to 10 units in its length. This is the missing side AB. It equals to 10 units in its length. So the parameter of quadrilateral ABCD equals to AB, that is 10, plus AD, that is 40, 10 plus 40 is 50, plus DC, that is 40, 50 plus 40 is 90, plus BC, that is 50. 90 plus 50 is 140. So in total, if you want to know that the perimeter of this quadrilateral ABCD is equal to 140 units in its length. And again, the perimeter of this quadrilateral ABCD is actually a right-angled trapezoid, is equal to 140 units in its length. In the next step, I will present to you another way to find out the length of this side AB. And again, we'll find out in a different method. We'll prove that AB equals to 10 units in its length. In order to find, so for that, we'll do a construction here. That is to say, from point B, we'll go perpendicular on PM. Again, from point B, we'll go perpendicular on PM. So actually, this angle equals to 90 degrees in its side, and this angle also equals to 90 degrees in its side, according to our construction. We will define the touching point of the perpendicular from point B and PM. This point is point S. So by doing this construction, we created the small quadrangle ABSP. Inside the small quadrangle ABSP, we have 1, 2, 3 right angles, and therefore this four-piece angle must be equal to 90 degrees in size, according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. So in quadrangle ABSP, we have 4 right angles, and therefore it is a right angle. So the small quadrangle ABSP is a right angle because it has 4 right angles. So by doing this construction, you can do the right triangle BSM. This is the right triangle BSM. It is very easy to see that those two right angles can go into each other according to angle side angle rule. We prove why those two right angles can go into each other. That is to say that the right triangle BSM can go into this right triangle M and C. So why those two right angles can go into each other? First of all, before I prove it, here this angle equals to 90 degrees, this angle equals to 90 degrees minus alpha, therefore this first angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. Therefore, this means angle must be equal to alpha. So why those two right angles can go into each other? Why the right triangle BSM can go into this right lower triangle and triangle M and C? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, the hypotenuses of those two right triangles are both equal to 25, and therefore they are equal to each other. We only found out that BM equals to 25, and we only found out that MC also equals to 25. So the hypotenuses of those two right triangles, they are both equal to 25, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we should prove that those two angles, and the side that is included between those two angles, that is side BM, and this side BSM, are corresponding equal to those two angles, and the side that is included between those two angles, that is side MC, and this side MNC. Therefore, those two right triangles can go into each other according to angle side angle rule. So if we found out that the upper right triangle BSM can go into the lower right triangle M and C. According to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that those two sides must be also equal to each other in their lengths, according to the sum rule that I have already mentioned, that corresponding sides in congruent triangles are equal to each other. Those two right triangles can go into each other, and therefore the two corresponding sides, that is to say NC and SM, must be also equal to each other in their lengths. But NC is 15, and therefore SM must be also equal to 15 units in its length, according to the rule that I mentioned. So SM must be also equal to 15 units in its length. What is the length of the missing line segment PS? It is very easy to see that PS in total equals to PM minus, again, PS equals to PM minus SM. So the missing side PS equals to PM minus SM. So the missing side PS equals to PM. PM is 25 minus SM. SM equals to 15. We just found out that SM equals to 15. I can see. So PS in total equals to 25 minus 15, that is 10. So we found out that PS equals to 10 units in its length. So in rectangle ABSP, side PS must be equal to the opposite side AB. Again, side PS must be equal to the opposite side AB in rectangle ABSP. But AB, PS is 10, and therefore the means inside AB must be also equal to 10 units in its length. So in the rectangle ABSP, the opposite sides are equal to each other. That is to say, PS equals to AB. PS equals to AB. But we already found out that PS equals to 10. And from this equation, 10 equals to PS equals to AB. We learned that AB also equals to 10 units in its length. So we found out that AB equals to 10 units in its length in two different methods. And the final answer to the question is that the perimeter of this quadrilateral ABCD, that is actually right angle trapezoid, is equal to 140 units in its length. So we finished with the first question. In the next step, I'll present you the second question of this lecture and we'll answer on the second question. Our task in this second question is to find out they are of this green shape. So in the drawing we have two semicircles. This is the big semicircle that contains this small semicircle. It is given us the question that line segment AC equals to 4 units in its length. This is line segment CB that equals to 6 units in its length. Again, our task is to find out the area of this green shape. Okay, so first of all, we find out the radius of this big semicircle. What is the radius of the big semicircle? We know that the diameter AB of this semicircle equals to AB, that is 4, plus BC, that is 6. 4 plus 6 is 10. So the diameter AB of this big semicircle equals to 10. We define the radius of this semicircle as capital R. The big semicircle, the radius of the big semicircle equals to capital R according to our definition. So capital R equals to AB, the diameter over 2. AB is 10 and 10 over 2 is 5. So we found out that the radius of the big semicircle capital R equals to 5 units in its length. We define the radius of the small semicircle as x. So we define the center of this big semicircle as O, and we define the center of this small semicircle as S. So SP is the radius of the small semicircle, is equals to x units in its length according to our definition. Likewise, SQ is also the radius of the small semicircle, is equals to x. In the next step, we'll join points S and C together by a straight line. What is the definition of line segment SC? Line segment SC starts from point S, that is the center of this small semicircle, and that's at point C, that is the point of the small semicircle itself. This is exactly the definition of a radius. Therefore, SC is the radius of this small semicircle, that is equals to x units in its length. Here we can implement rule 1. Why? Because we have the radius SC that is drawn to point C, that is the point of tendency of tangent AB with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius CS. If AB is perpendicular to CS, it means that this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to rule 1. In the next step, we will do another construction. That is to say, from point P, that's actually the touching point between the small semicircle and the big semicircle. So from point P, we will draw perpendicular on AB. Again, from point P, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and side AB. This point is point M. Actually, there is a problem with the drawing itself because I must complete the quarter circle to a circle, and it doesn't have not have enough space to complete it. So a circle. Okay. So we define the touching point of the perpendicular from point P and AB. This point is point M. So what is the length of this line segment? Line segment AM. First of all, we have here the radius SP that equals to x. The radius SP is drawn to point P. That is the point of tendency of tangent AP with this small semicircle. And whenever your radius is drawn to the point of tendency, then tangent AP will be perpendicular to the radius PS. If MP is perpendicular to PS, it means that this angle equals to 90 degrees according to rule 1. So in the small quadrilateral PSCM, we have 1, 2, 3 rectangles, and therefore this fourth angle must be equal to 90 degrees in its size, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, in quadrilateral PMCS, we have 4 rectangles, and therefore it is a rectangle. This is the small quadrilateral PSMC, that is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PSCM, side PS must be equal to the opposite side MC, but PS equals to x, and therefore the opposite side MC must be also equal to x units in its length. Likewise, according to the sum rule in the sum rectangle PSCM, side SC must be equal to the opposite side PM, but SC is x, and therefore the opposite side PM must be also equal to x units in its length. So we found out that quadrilateral PSCM is a square. Okay, what is the length of this missing line segment? Line segment CO. From the drawing, it is very easy to say that CO in total equals to CB minus OB. Repeat again. The small line segment CO equals to CB minus OB. So CO in total equals to CB is 6 according to what is given in the question, minus OB. OB starts from point O, that is the center of the big semicircle, and that's at point B, that is the point on the big semicircle itself. This is exactly the definition of radius. Therefore, OB is the radius of the big semicircle, that is 5. So in total, CO equals to 6 minus 5, that is 1. So CO equals to 1 unit in its length. CO equals to 1 unit in its length. So, in the next step, we'll complete the semicircle to a circle. So, cannot do it correctly. So, don't have enough space the lower side. So consider it as a circle. So completed the semicircle to a circle, and then we'll extend PM, we extend tangent PM by straight line until it touches the circle. We define the touching point of the extended tangent PM with this circle. This point is point N. PM as a tangent, it is absolutely a straight line. We extended the straight line PM, extended tangent PM, that is a straight line by straight line. We extend the straight line by straight line, the result is the straight line. So PN is a straight line. So if we focus on the right side of the straight line PM, if we focus on the right side of the straight line PN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line PN at point M? We have this angle that is 90 degrees, plus the missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So angle CMN equals to 90 degrees in its size. So in the drawing we have a circle. Point O is the center of this big circle. From point O, that is the center of this big circle, we have perpendicular OM on chord PN. Again, from point O, that is the center of this semicircle, of this big circle, we have perpendicular OM on chord PN. And remember, from the center of the circle, we have a perpendicular on any chord. The perpendicular OM will bisect chord PN according to rule 15. And again, a perpendicular that is drawn from the center of the circle towards any chord will bisect the chord according to rule 15. So, according to rule 15, a perpendicular from the center of a circle towards any chord will bisect the chord. In the drawing, we have a circle. Point S is the center of the circle. From point S, that is the center of the circle, we have perpendicular ST on chord MN. Again, from point S, that is the center of this circle, we have perpendicular ST on chord MN. And according to this rule, rule 15, perpendicular ST bisect chord MN. If ST bisects chord MN, it means that at point T, chord MN has been bisected into two halves. The first half is MT, and it is of course equal to the second half, that is Tn, and each half must be equal to Mn over 2, because Mn has been bisected. So today we found out that Mt equals to Tm equals to Mn over 2. So you can actually implement rule 15 in our drawing. Why? Because in our drawing, so as I mentioned before, from the center of this big circle, that is to say from point O, we have perpendicular OM on chord PN. And according to rule 15, perpendicular OM bisect chord PN. That is to say, at point M, PN has been bisected into two halves. The first half is PM, and it is of course must be equal to the second half MN. So, according to rule 15, perpendicular OM bisect chord PN. That is to say, at point M, PN has been bisected into two halves. The first half of PN is PM, and it is of course must be equal to the second half, that is MN. But we already found out that PM equals to X. So we can write here that PM equals to X. And from this equation, X equals to PM equals to PN. We derive that MN also equals to X units in its length. Again, MN equals to X units in its length. MN equals to X units in its length. So here, you can implement all 24. Why? Because we have here, this is called AB. It's actually the diameter of the big semicircle, called AB. Intersects with chord PN at point M. Again, chord AB intersects with chord PN at point M. And remember, you have two chords that intersect with each other inside the circle. You can implement all 24. Repeat again, on all 24. All 24 is true in any circle. So, in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. AO times BO equals to CO times DO. Again, in the domain we have a circle. This is called AB. This is called AB that intersects with chord CD at point O. Again, chord AB intersects with chord CD at point O. So in this domain, whenever we have two chords that intersect with each other, the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement all 24 in our domain. In our domain, as I already mentioned before, we have chord AB that intersects with chord PN at point M. So it is known. Now we're going. We have chord AB. Intersects with chord PN. At point M. So all the requirements of all 24 are satisfied, and therefore we can implement here all 24. According to rule 24, the following equation is true. AM times MB equals to PM times MN. Again, according to rule 24, the following equation is true in our drawing. AM times MB equals to PM times MN. But first of all, we have to find out the length of AM. What is the length of AM? From the drawing, it is very easy to see that AM in total equals to AC minus MC. Again, AC minus MC equals to AM. So write it down. I have found out that AM in total equals to AC minus MC. So in total, AM equals to AC. AC is 4 according to what is given us the question. Minus MC. We already found out that MC equals to X. So in total, AM equals to 4 minus X. Write it down. AM equals to 4 minus X units in its name. So we substitute AM by 4 minus X times MB. What is the length of MB? MB in total equals to X plus 6. Again, MB in total equals to MC, that is MB in total equals to MC, that is X, plus CB, that is 6. So in total, MB equals to X plus 6 units in its name. So substitute MB by X plus 6. And it is equals to PM times MN. PM equals to X, MN also equals to X. X times X is X squared. So in total we should find out that 4 minus X times x plus 6 equals 4 minus x times x plus 6 equals to x squared. Here we will open the brackets of this side of the equation and we get that 4 times x is 4x plus 4 times x is 24 plus minus x times x is minus x squared and minus x times 6 is minus 6x. Minus x times 6 is minus 6x equals to x squared. So in total, on this side of the equation we have 4x minus 6x is minus 2x plus 24 minus x squared equals to x squared. So minus x plus 24 minus x squared equals to x squared. Here we will add x squared to the equation and finally get that in this side of the equation we left only with 24 minus 2x equals to x squared minus x squared is 0. X squared plus x squared is 2x squared. So in total we found out that 24 minus 2x equals to 2x squared. Here we let 2x and subtract 24 simultaneously to this equation. And we get that 2x squared plus 2x minus 24 equals to 0. But again, we found out that 2x squared plus 2x minus 24 equals to 0. Here we divide this equation by 2 and finally get that 2x squared over 2 is x squared plus 2x over 2 is 2x over 2 is x, so it is x squared plus x minus 24 over 2 is minus 12 equals to 0 over 2 is 0. So in total we found out that x squared plus x minus 12 equals to 0. So actually, this is a quadratic equation. And the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus x minus 12 equals to 0, the variable that we are looking for is x. X is the radius of this small semicircle. So write it down. The variable that we are looking for is x, and x is the radius of the small semicircle. The coefficient a equals to 1, the coefficient b equals also to 1, and the coefficient c equals to minus 12. The only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x. In this way we find out the value or the values of x is actually the radius of the small semicircle. So we do it now and get that here x equals to minus b. B is minus 1 and therefore minus b is minus 1 plus minus square root of b squared. B is 1, so b squared is 1 squared, it is 1. Minus 4 times a times c, so it is minus 4 times a. A is 1, so minus 4 times 1 is minus 4 times c. C is minus 12, and minus 4 times minus 12 is plus 48. So in total, minus 4 times ac equals to plus 48 over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, we found out that x equals to minus 1 plus minus 1 plus 48 is 49, and the square root of 49 is 7 over 2. So if you found out that x equals to minus 1 plus minus 7 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to minus 1 minus 7 over 2. Minus 1 minus 7 is minus 8, and minus 8 over 2 is minus 4. So in total, if you want to know that according to the first solution for x equals to minus 4. So we mentioned before, x is the radius of this small semicircle. That is to say, x is a length, and x as a length, it must be a positive number. But minus 4 is a negative number. Therefore, x can never be equal to minus 4, that is a negative number. X must be a positive number. So we can set the solution. So we left only with the second solution for x. The second solution for x is as follows: x equals to minus 1 plus 7 over 2. Minus 1 plus 7 is 6, and 6 over 2 is 3. So according to the second solution for x is the radius of this small semicircle, and it is equals to 3 units in its length. So x equals to 3. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape in total is equal to the area of the big semicircle and you know that the radius of the big semicircle is 5. Minus the area of this small semicircle. We just now found out that the radius of the small semicircle is 3. And again, if we found out that the area that we are looking for in this question, that is the area of this green shape, in total it is equals to the area of the big semicircle, if radius 5, minus the area of the small semicircle, if radius 3. The area of the big semicircle, if radius 5, is equals to pi times the radius squared over 2. That is to say it is pi times 5 squared over 2. Minus the area of the small semicircle. The radius of the small semicircle is 3, therefore the area of the small semicircle must be equal to pi times the radius squared, that is 3 squared over 2. So in total, 5 squared is 25. So in total, this expression equals to 25 pi over 2 minus the area of the small semicircle. 3 squared is 9, so it is 9 pi over 2. 25 pi minus 9 pi is 16 pi over 2. 16 pi over 2 is 8 pi. In terms of numbers, is equal to 25.13 square units in its size. If you're going to show out that the area that we're looking for in this question, it is the area of this green shape, is equal to either 8 pi square units in its size, or in terms of numbers, it is equal to 25.13 square units in its size. So we finished to answer the second question. In the next step, I will summarize the lecture. We start with the first question, of course, and then repeat the solution of the second question. Our task in the first question is to find out the area of this quadrilateral ABCD. It is given us the question that this is line segment BQ, this is equals to 10 units in its length. This is line segment PQ, this is equals to 20 units in its length. This is line segment QC, this is equals to 40 units in its length. This is a right angle, this is a right angle, and this is also a right angle. Again, our task is to find out the perimeter of this quadrilateral ABCD. What is the definition of a perimeter? Perimeter is the sum of the four side lengths of a quadrilateral. So the perimeter of this quadrilateral ABCD equals to the sum of its four side lengths. That is to say, it is AB plus AD plus DC plus CB. Okay. So in the first step, we did a construction. That is to say, from we draw perpendicular on side AD at point P. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. In the next step, we extended the perpendicular on point P by a straight line until it touches side BC. We define the touching point of the extended perpendicular from point P, and this side BC, this point is point M. Okay. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. Those two angles are defined as one-sided interrogants. The sum of those two one-sided interrogants is 180 degrees. Whenever you have sum of two right angles of two one-sided interrogants is equal to 180 degrees, the two angles must be located between parallel lines. That is to say, the sum of those two one-sided interrogants is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, AB is parallel to PM according to Rule 18. So a bit quicker on Rule 18. According to Rule 18, if the sum of two one-sided interrogants is equal to 180 degrees, then they must be located between parallel lines. In the drawing, we have those two angles alpha and beta are defined as one-sided interrogants. If the sum of those two angles is equal to 180 degrees, that is to say, if alpha plus beta equals to 180 degrees, then they must be located between parallel lines. That is to say, line A is parallel to line B. So if alpha plus beta equals to 180 degrees, then line A is parallel to line B. So you can implement Rule 18 in our drawing, because in our drawing, the sum of those two one-sided interrogants is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, AB is parallel to PM. Again, according to Rule 18, AB is parallel to PM. Likewise, the sum of those two one-sided interrogants is equal to 180 degrees, and therefore those two one-sided interrogants must be located between parallel lines. That is to say, PM is parallel to DC. Again, PM is parallel to DC according to Rule 18. Likewise, the sum of those two one-sided interrogants is also equal to 180 degrees, and therefore those two one-sided interrogants must be located between parallel lines. That is to say, AB is parallel to DC according to Rule 18. Again, AB is parallel to DC. So in conclusion, we found out all the three line segment AB, PM, and DC are parallel to each other. So AB is parallel to PM, is parallel to DC according to Rule 18. And whenever you have three or more parallel lines, like here we have line A is parallel to AB is parallel to PM is parallel to DC, those three parallel lines are connected together by AD and BC. So whenever you have three or more parallel lines that are connected together by other two line segments, like here AD connects the three parallel lines here, and BC also connects the three parallel lines together by this straight line. Then a special relationship exists between the two parallel lines AD and BC that connects the three parallel lines together. The relationship is as follows. AP over PD equals to BM over MC according to the basic proportionality theorem. Again, according to the basic proportionality theorem, Whenever you have three or more parallel lines that are connected together by two other line segments, then the following relationship exists between the two line segments that connects the three parallel lines together. The relationship is as follows. AP over PD equals to BM over MC, according to basic proportionality theorem. And according to the basic proportionality theorem, the following relationship exists between the two line segments AD and BC that connects the three parallel lines together. The relationship is as follows. AP over PD equals to BM over MC. It's given us the question that AB equals to PD. So if we define AP as x, then PD must be also equal to x because they are equal to each other. So we substitute AP by x and PD. We substitute AP by x and PD also by x. And this equals to BM over MC. X over x is 1. So 1 equals to BM over MC. Here we multiply this equation by MC and found out that MC equals to BM. BM equals to MC. That is to say, at point M, BC is bisected into two halves. Again, at point M, side BC is bisected into two halves. The first half is BM, the second half is MC. Of course, the first half BM must be equal to the second half MC, and each half must be equal to BC over 2 because BC is bisected into two halves. So at point M, side BC has been bisected into two halves. The first half is BM, and it is of course must be equal to the second half, that is MC, and each half must be equal to BC over 2 because BC has been bisected into two halves. So BM equals to MC equals to BC over 2. What is the value for BC? BC in total equals to 10 plus 40, that is 50. Again, BC in total equals to 10 plus 40, that is 50. So BC is 10 plus 40, that is 50 over 2. 50 over 2 is 25. So from this long equation, we derive that BM equals to MC equals to 25. So BM equals to 25 units in its length, and MC also equals to 25 units in its length. So in the next step, we focused on the green right triangle PQM. First of all, what is the length of QM? We know that BM is 25. BM must be O equals to QM. Okay. And the missing side QM equals to BM minus BO. Again, QM equals to BM. The missing side QM equals to BM minus BQ. BM minus BQ. So QM equals to BM, that is 25, minus BQ, that is 10. So in total, QM equals to 25 minus 10, that is 15. So QM equals to 15 units in its length. In the next step, we implemented the Pythagoras theorem on this right green triangle PQM. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle PQM, PM squared, that is the square of the hypotenuse, equals to PQ squared plus QM squared. Repeat again, the right green triangle PQM, PM squared, that is the square of the hypotenuse, equals to QM squared plus QP squared. PM is the missing side, so leave it as it is, so it is PM squared equals to QM squared. QM is 15, therefore QM squared is 15 squared, that is 225, plus PM squared. PM plus QM is 15, therefore QM squared is 15 squared, that is 225, plus PQ squared. PQ is 20, therefore PQ squared is 20 squared, that is 400. So in total, we have found out that PM squared equals to 225 plus 400, that is 625. So PM squared equals to 625. We took a root out of this equation and found out that PM equals to the square root of 625, that is 25. So the length of the hypotenuse PM of the green right triangle PQM is equal to 25 units in its length. In the next step, we did another construction, that is to say, from point M, we do perpendicular on DC. Again, from point M, we do perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point M and DC. This point is point N. By doing this construction, we can derive quadrilateral PM and D. Inside quadrilateral PM and D, we have 1, 2, 3 right angles. This is right angle according to our construction. So we have 3 right angles in quadrilateral MPDN. The sum of 3 right angles is 270 degrees. 270 degrees plus the size of this fourth angle in total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth angle must be equal to 90 degrees in its size. So in quadrilateral PM and D we have 4 right angles, and therefore it is a left angle. Quadrilateral PM and D is a left angle because it has 4 right angles. In the next step, we defined the size of this angle QPM as alpha. So in the green triangle PQM, the green triangle PQM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. It is the sum of the angles in any triangle. Therefore this first missing angle must be equal to 90 degrees in its size. So BC is one side of quadrilateral ABCD. So BC is one side of a quadrilateral, it is absolutely a straight line. So BC is a straight line, so if you focus on the right side of the straight line, BC is point M. Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have on the right side of the straight line BC at point M? We have this angle that is 90 degrees minus alpha, plus this angle that is 90 degrees, plus the missing angle. In total, the sum of those 3 angles must be equal to 180 degrees according to rule 3. So 90 degrees minus alpha plus 90 degrees is 180 degrees minus alpha. So 180 degrees minus alpha plus the missing angle in total must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to alpha. Why? Because 180 degrees minus alpha plus alpha is 180 degrees. That is the sum of the angles of the right side of the straight line BC at point M according to rule 3. Therefore, this missing angle must be equal to alpha degrees in its size according to rule 3. So in the right triangle MNC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha according to the same rule that said that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the right green triangle PQM is similar to, congruent to this right lower triangle MNC. Why those two right triangles are congruent to each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two sides are both equal to 25, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we shall find out that those two angles and the side that is included between those two angles, that is side PM in the right triangle PQM, are corresponding equal to those two angles, and the side that is included between those two angles, that is side MC on this right triangle MNC. And therefore, those two right triangles can go into each other according to angle side angle rule. So again, we found out that the right triangle PQM congruent, this is the sign of congruent, to the right triangle MNC according to angle side angle rule. And from the fact that those two right triangles are similar to each other, we derive that those two sides also equal to each other according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two sides must be also equal to each other in their lengths. But PQ is 20, therefore MN must be also equal to 20 units in its length. Likewise, according to the same rule, those two sides must be also equal to each other in their lengths. But QM is 15, and therefore MN must be also equal to 15 units in its length. So in total, DC equals to 25 plus 15, that is 40. So we already found out that AB is parallel to DC. Again, AB is parallel to DC. And therefore, quadrilateral ABCD is a trapezoid. Because a trapezoid is a quadrilateral with one pair of parallel sides. AB is parallel to DC, and therefore quadrilateral ABCD is a trapezoid according to the definition that I mentioned. So we have a trapezoid that is actually a right angle trapezoid because those two angles are right angles. So in the drawing you have right angle trapezoid. We can implement here the trapezoid mid-segment theorem. This is the mid-segment PM. Mid-segment PM bisect AD. At point P, AD is been bisected into two halves. The first half is AP, the second half is PD. And of course, the first half equals to the second half. Likewise, at point M, BC has been bisected into two halves. BM equals to MC. So actually, this is line 7 PM that bisects the leg AD, and line 7 PM also bisects the leg BC. The two parallel lines AB and DC are defined as the bases. So in conclusion, we can say that PM bisects both the leg AD and the leg BC of this trapezoid ABCD. And therefore PM is defined as the mid-segment of trapezoid ABCD because it bisects leg AD and bisects leg BC. And according to trapezoid mid-segment theorem, the following equation is true. What is the length of PM? PM equals to the sum of its two parallel bases of trapezoid ABCD, that is to say AB plus DC over 2. And again, according to the mid-segment trapezoid theorem, PM equals to AB plus DC over 2. That is to say it is the sum of its two parallel bases, it is AB plus DC over 2. And again, according to the trapezoid mid-segment theorem, mid-segment PM or line 7 PM, the mid-segment of trapezoid ABCD equals to the sum of its two parallel bases, that is actually AB plus DC over 2. We already found out that PM equals to 25, so we can substitute PM by 25, and it is equals to AB. AB is the missing side, so we leave it as it is, plus DC. We already found out that DC in total equals to 25 plus 15, that is 40. So DC is 40. So we substitute DC by 40 over 2. So in total we found out that 25 equals to AB plus 40 over 2. Here we multiply this equation by 2 and finally found out that 25 plus times 2 is 50. So 50 equals to AB plus 40. Here we subtracted 40 from this equation and finally found out that AB equals to 50 minus 40, this is 10. So this inside AB equals to 10 units in its length. Actually, we found the perimeter of trapezoid ABCD because AB is 10 plus AD, that is 40, 10 plus 40 is 50, plus DC, that is 40, 50 plus 40 is 90, plus BC, that is 50, 90 plus 50 is 140. So in total we should know that the perimeter of trapezoid ABCD, the quadrilateral ABCD, equals to 140 units in its length. In the next step, I presented to you another way to find out that AB equals to 10 units in its length. In the first way, we relied on the trapezoid mid-segment theorem in order to find out that AB equals to 10. In the next step, I presented to you a second method to find out that AB equals to 10 units in its length. According to the second method, we did the construction, that is to say from point B, we do perpendicular on PM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and PM. This point is point S. By doing this construction, we get the quadrilateral ABSP. In quadrilateral ABSP, we have 1, 2, 3 angles, 3 right angles, and therefore this fourth angle must be equal to 90 degrees inside. So in quadrilateral ABSP, we have 4 angles. In quadrilateral ABSP, we have 4 right angles, and therefore quadrilateral ABSP is a rectangle. So in the right triangle BSM, this angle equals to 90 degrees minus alpha. This angle equals to 90 degrees, and therefore this first angle must be equal to alpha. Because why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles in a triangle. Therefore, this first angle must be equal to alpha. In the next step, we prove that those two right angles can can go into each other according to angle side angle rule. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. Those two hypotenuses are both equal to 25 degrees and they are both equal to 25 units and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees on alpha and therefore they are equal to each other. So if you prove that those two angles and the side that is included between those two angles, that is side BM, in the right triangle, this right triangle BSM are corresponding equal to those two angles, and the side that is included between those two angles, that is side MC in the right triangle, this right triangle MNC. Therefore, those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that side SM in the right triangle BSM is equal to side NC of the right triangle MNC. According to the rule that corresponding sides and can go into triangles are equal to each other. Those two triangles can go into each other, and therefore the two corresponding sides SM and NC must be also equal to each other in their lengths. But we have already found out that NC equals to 15 units in its length, and therefore MS, the corresponding side MS, must be also equal to 15 units in its length. So in total, SP equals to PM, that is 25, minus SM, that is 15. Again, PS equals to PM minus SM. So PS equals to PM, that is 25, minus SM, that is 15. So in total, PS equals to 25 minus 15, that is 10. So PS equals to 10 units in its length. So in the rectangle ABSP, the opposite sides are equal to each other. That is to say, side PS must be equal to the opposite side AB, but PS is 10, therefore the opposite side AB must be also equal to 10 units in its length. So we proved that two different ways that AB must be equal to 10 units in its length. And the perimeter of this right angled trapezoid ABCD is equal to 140 units in its length. So we finish with the first question. The next step, I'll repeat on the solution on the second question. In this second question, our task is to find out the area of this green shape. So in the drawing we have two semicircles. This is the big semicircle that contains this small semicircle. It is given us the question that this is line segment AC, this is equals to 4 units in its length. This is line segment CB, this is equals to 6 units in its length. Again, our task is to find out the area of this green shape. So first of all, we found the radius of this big semicircle. We know that the diameter AB in total equals to 4 plus 6, that is 10. The diameter AB over 2 is the radius of this big semicircle. So the diameter of the big semicircle is defined as capital R. Capital R equals to AB, the diameter AB over 2. AB is 10, and the radius is AB over 2, that is 10 over 2, that is 5. So in total, we found out that the radius of this big semicircle is equal to 5 units in its length. R, capital R equals to 5. That is the radius of the big semicircle. In the next step, we define the center of this big semicircle. This point is point O. Likewise, we define the center of this small semicircle. This point is point S. We already found out that the radius of this big semicircle equals to 5 units in its length. We define the radius of this small semicircle as x. So it was a very easy question, because the only missing variable is here is the radius of this small semicircle. After we found out the radius of this small semicircle, we only answered on the question, because the area of this green shape equals to the area of the big semicircle minus the area of this small semicircle. And the area of this small semicircle equals to pi times the radius square over 2. So the only missing side, the only missing variable in this question is x. So we find out the value of x, we solve the question. Because the area of this green shape equals to the area of the big a semicircle, that is pi times pi square over 2, minus the area of this small semicircle, that is pi x square over 2. Okay. So here we have, we join points S and C together by straight line. Point S is the center of this small semicircle. Point C is the point on the small semicircle itself. Therefore, SC is the radius of this small semicircle. This is equal to x units in its length according to our definition. The radius SC is equal to S. The radius SC is equal to x. The radius SC is drawn to point C. That is the point of tendency of tangent AB with this small semicircle. Whenever your radius is drawn to the point of tendency, then AB will be perpendicular to the radius CS. If AB is perpendicular to CS, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in the next step, we did another construction, that is to say, from point P, we do perpendicular on AB. Again, from point P, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and AB. This point is point M. What is the definition of line segment MP? Line segment MP is tangent to this small semicircle at point P. Therefore, MP is a tangent. And here we have the radius SP is equals to x. The radius SP is drawn to point P. That is the point of tendency of tangent MP with this small semicircle. And whenever your radius is drawn to the point of tendency, then tangent MP will be perpendicular to the radius SP. If MP is perpendicular to SP, it means that this angle equals to 90 degrees according to rule 1. So in total, in the small quadrangle PSCM, we have 1, 2, 3 arteries. Therefore, this fourth angle must be equal to 90 degrees inside according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. So quadrangle PSCM is 4 arteries, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PSCM, side PS must be equal to the opposite side MC. But PS equals to x, it is the radius of the small semicircle, and therefore MC must be also equal to x units in its length. Likewise, according to the symbol, in the sum of rectangle PSCM, side SC must be equal to the opposite side PM. But SC is x, and therefore the opposite side PM must be also equal to x units in its length. So actually, we found out that quadrangle PSCM is not a rectangle but a square, because all sides are equal to each other, each of them is equal to x. What is the length of this line segment? Line segment AM. AM equals to AC, that is 4, minus MC, that is x. Again, AM equals to AC minus MC. So AM equals to AC, that is 4, minus MC, that is x. So in total, AM equals to 4 minus x units in its length. What is the length of this missing small line segment CO? CO equals to CB minus OB. So CO equals to CB, that is 6, minus OB, that is 5, that is the radius of the big semicircle. So in total, CO equals to 6 minus 5, that is 1. In the next step, we did a construction, that is to say, we completed this semicircle to a circle, and then we extended tangent PM by straight line until it touches the circle at point N. So, tangent PN, as a tangent, it is absolutely a straight line. When we extended the straight line PN by straight line, the result PN must be also a straight line. So PN is a straight line. If you focus on the right side of the straight line, PN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of PN at point M? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the drawing, we know that point O is the center of this big circle. So from the center of this big circle, that is point O, we have perpendicular OM on chord PN. Again, from the center of this big circle, that is point O, we have perpendicular OM on chord PN. And remember, from the center of the circle, we have a perpendicular towards any chord, it will bisect the chord. According to rule 15. So, repeat quickly on rule 15. According to rule 15, a perpendicular from the center of a circle towards any chord will bisect the chord. In the domain we have a circle, this is point S, that is the center of the circle. So from the center of the circle we have perpendicular ST on chord MN. And according to this rule, rule 15, perpendicular ST bisect chord MN. That is to say, perpendicular ST divides chord MN into two halves. The first half is empty, and it of course equals to the second half of MN, that is Tn, and each half must be equal to Mn over 2 because Mn has been bisected into two halves. So in total we should find out that according to rule 15, perpendicular ST bisect chord Mn. That is to say, Mt equals to Tm equals to Mn over 2. So we can actually implement rule 15 in our drawing. In our drawing, as I already mentioned before, we have here from the center of this big circle we have perpendicular OM on chord PN. According to rule 15, perpendicular OM bisect chord PN. That is to say, it divides chord PN into two halves. The first half is PN, and it must be equal to the second half MN. So perpendicular OM bisect chord PN. The first half is PN, it must be equal to the second half MN. Again, perpendicular OM bisect chord PN into two halves. The first half is PM, it is of course equals to the second half MN. But PM equals to X. So we can write here that PM equals to X, and from this equation X equals to PM equals to MN, we will derive that Mn also equals to X units in its length. This is 9/7 Mn, this is also equals to X units in its length according to rule 15. So in the domain we have, this is called AB, that is the diameter of this big circle. Chord AB intersects with chord PN at point M. Again, chord AB intersects with chord PN at point M. And remember, we have two chords that intersect with each other. Inside the circle, you can implement rule 24. So I repeat quickly on rule 24. According to rule 24 is true in any circle. So in any circle, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times BO equals to CO times DO. Again, we have chord AB that intersects with chord CD at point O. So in this domain, the following equation is true, that AO times OB equals to CO times OD. So we can implement rule 24 in our drawing. Well, because in our drawing, we have chord AB that intersects with chord PN at point M. And again, in our drawing, we have chord AB that intersects with chord PN at point M. And therefore, we can, all the requirements of rule 24 are satisfied, and therefore we can implement here rule 24. According to rule 24, the following equation is true, that AM times AMB equals to PM times MN. Again, according to rule 24, the following equation is true, that AM times AMB equals to PM times MN. So again, according to rule 24, the following equation is true, that AM times MB equals to PM times MN. AM equals to 4 minus X. So substitute AM by 4 minus X. MB in total equals to X plus 6. So we substitute MB by X plus 6. And it's equals to PM. PM is X times MN, it is also X. So PM times MN in total it is X times X, it is X squared. So in total we should find out that 4 minus X times X plus 6 equals to X squared. We open the brackets of this expression, and here we have 4 times X. 4 times 6 is 24. Minus X times X is minus X squared, and minus X times 6 is minus 6X equals to X squared. So in total we should find out that 4X plus 24 minus X squared minus 6X equals to X squared. 4X minus 6X is minus 2X. We have here plus 24 minus X squared equals to X squared. So in total 4X plus 24 minus x squared equals to x squared. Here we added x squared to this equation, so here we have x squared plus x squared is 2x squared. Here x squared will get cancelled, and left only with minus 2x plus 24 equals to 2x squared. And again, if you found out that 24 minus 2x equals to 2x squared. Here we did 2x and also subtracted 24 simultaneously from this equation, and finally found out that 2x squared plus 2x minus 24 equals to 0. Here we divided this equation by 2 and finally found out that 2x squared over 2 is x squared, plus 2x over 2 is x, and minus 24 over 2 is minus 12 equals to 0 over 2 is 0. So in total we found out that x squared plus x minus 12 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus 4 of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus x minus 12 equals to 0, the variable that we are looking for is x, and x is the radius of the small semicircle. The coefficient a equals to 1, the coefficient b equals also to 1, and the coefficient c equals to minus 12. So the only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x, and in this way we find out the value of the values of x, and repeat that x is the radius of the small semicircle. So we did it, and we found out that x equals to minus b. B is 1, therefore minus b is minus 1 plus minus 4 of b squared. B is 1, so b squared is 1 squared, it is 1, minus 4 times a times c. So it is minus 4 times a is 1, so it is minus 4 times 1, that is minus 4 times c. C is minus 12, so minus 4 times minus 12 is plus 48. So in total, minus 4 times a times c is plus 48. So inside the root we have 1 plus 48 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total we found out that x equals to minus 1 plus minus 1 plus 48 is 49, and the square root of 49 is 7. So in total we found out that x equals to minus 1 plus minus 7 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to minus 1 minus 7 over 2. Minus 1 minus 7 is minus 8, and minus 8 over 2 is minus 4. So the first solution for x is that x equals to minus 4. But because of the fact that x is the length of the radius of the small semicircle, x as a length, it must be a positive number. But minus 4 is a negative number. So x can never be equal to minus 4, that is a negative number, it must be a positive number. So we cancel the first solution for x, and we take into account on the second solution for x. The second solution for x is as follows: x equals to minus 1 plus 7 over 2. Minus 1 plus 7 is 6, and 6 over 2 is 3. So if we found out that the radius of this small semicircle x equals to 3 units in its length. Our test is to find out they have this green shape. From the drawing, it is very easy to see that the area of the green shape in total equals to the area of the big semicircle minus the area of the small semicircle. Repeat again, the area of the green shape in total equals to the area of the big semicircle, if radius 5, minus the area of the small semicircle, if radius 3. Therefore, the area of the big semicircle must be equal to pi r squared over 2. R is 5, so it is pi times 5 squared over 2, minus the area of the small semicircle, if radius 3. Therefore, the area of the small semicircle must be equal to pi times 3 squared over 2. So in total, the area of the green shape equals to pi times 5 squared over 2 minus pi times 3 squared over 2. 5 squared is 25, so in total this expression equals to 25 pi over 2 minus 3 squared is 9, so in total this expression equals to 9 pi over 2. 25 pi over 2 minus 9 pi over 2 is 16 pi over 2. 16 pi over 2 is 8 pi. 8 pi in terms of numbers is equals to 21 minus 1, 25 minus 1, 3. So in total we found out that the area that we are looking for in this equation, that is the area of this green shape, is equal to either 8 pi square units in size, or in terms of numbers, it is equal to 25 minus 1, 3 square units in size. Okay, thank you very much.